Now I'll come to the next point about modifications of the basic gradient descent learning algorithm, how you set the learning rate and so on. So kind of the details of how we do the optimization. So it's good to illustrate that by a small kind of toy example. So we have an example where we only have one training point, and we have this kind of scalar network again with a linear output unit. So that means that the network output is just, and we set the input just to 1 and the target to 1.5, so it's regression now. So the output of the network is simply W1 times W2. And then we have a squared error, so we look at the difference of this weight 1, weight 2 to 1.5, and then we also add a penalty to the square length of the weight. So that will give these two kind of bananas and kind of the minimums of these two yellow areas you have in the plot. And we, of course, we have this kind of symmetry, which is kind of always in these networks, that we can actually change the sign of both weights, and then we get the same output mapping. So let's look at let's look at gradient descent on this. So we can actually, since we only have two parameters, we can illustrate this, and we can actually take a whole grid and compute the gradient in each of these grid points. And you can see it works. The gradient is always pointing towards kind of the minimum. So let's try to use our description here, where we take small steps opposite the gradient, and we just choose a value for eta to be constant, to be 0.25, and you can see that it takes some time to reach the minimum. And we are kind of doing this thing that would also happen if we kind of let a ball go on the side of it like a tube, and then it will kind of go from one side to the other and only slowly kind of going in the right direction. So we waste a lot of time going up and down the hill here, and this is kind of what we in these conjugate gradient methods is actually to avoid doing this kind of designed to avoid doing this kind of backtracking. Okay, but it looks like here that we actually have a too small step size, so why not try to increase the step size? So we just add 0.1 to the step size, and now you can see that suddenly we have actually a too large step size, so we actually kind of have a tendency to really go too far up the hill on the other side, and we simply cannot get down to the minimum because we are always oscillating, overshooting our target. So a method that actually takes this into account by actually using the curvature, so that is calculated by taking the second derivative, calculating so-called Hessian, which is in this case a 2 by 2 matrix, but in general is the number of parameters times the number of parameters matrix. We can kind of replace with Raphson rule, we can replace the kind of scalar learning rate by the inverse of this Hessian matrix. And that is actually working really, really well if we are close to having a quadratic minimum. But many times we don't have quadratic minimum, and we can also have the kind of the curvature goes the other way, and this happens in the corner of the plot, and you can see then actually we are moving in the wrong direction. So it means that Newton's method is really computational intensive, because you have to compute the inverse of this very large matrix. You cannot store this matrix with deep learning models that have millions of parameters, but still it gives you some intuition about kind of the right thing to do, actually kind of the right step size to use. And a lot of the kind of more efficient algorithms are partly inspired by kind of a Newton method. So they try to actually make a cheaper way to achieve some of the same things as the Newton method. One thing to kind of avoid this kind of oscillatory behavior is to kind of remember where you went in the previous step. So this is called a momentum method. So you can see you kind of keep a memory of what the gradients were in the previous steps by this m parameter, and then you only modify this by having this alpha in front, which is below 1. So you kind of slowly forget your old gradients and then adding kind of the new steps, and then your update will kind of be a combination of the current gradient descent direction and then our memorized gradient descent. And in this example you can see that it gives this kind of more smooth behavior. We can also have a noisy gradient. As I said, this is something we get when we have mini batch learning, and we can also simply add noise, and you get something like this. Here it looks like it's not really a good idea, but in general when we scale it to large systems, it turns out that actually stochastic gradient methods are very nice. So this is already here the mini batch method. So the idea is, as I said already, that we calculate the gradient on not the whole data, but on a subset of the data. And this means that this means several things. First of all, it means that maybe in the beginning of training that you actually are so far off because you initialize some random parameter setting. So you actually only need a few data to kind of give you a kind of a general sense of where you want to go. Secondly, as I talked about in the beginning, that actually having a stochastic gradient introduces some noise that can actually help you get out of saddle points and local minima. And then the third thing is that actually if you have large data sets and you use a GPU, you might not be able to store all your data in your GPU memory, and therefore it's nice to actually only have to store kind of a subset of the data. So for example, with MNIST, if we put 100 samples in our mini batch, then we need to use we can make 600 updates of the parameters before we have done one epoch, one kind of cycle through all the data. And also an important thing is that we actually need to change the step size throughout learning. And I'll come back to that in the next few slides, where I go through Adam, which is one of these kind of popular implementations of these kind of momentum gradient, stochastic gradient descent methods. Yes. So here's just an example of how it looks if we, with our running example from before. This is after one update. We can actually already try to start to see that there's some structure in the parameters. We start from kind of random Gaussian parameters. This is after one update, so you can see after one epoch, so that's 600 updates. You can see already starting to picking up a signal where we actually have the kind of the actual digits in the image. And now after 2 epochs, 3 epochs, 4 epochs, 5, 10, and 50, and then we stop here. And now you can see we have this pattern where we kind of see we have kind of edge detectors, this black and white thing that kind of picks up kind of parts of the digits. So a little bit here in the end about this Adam algorithm. So you can see if we kind of scroll down, we can see we have this GT term is kind of the gradient. So that was this gradient of the cost function of the mini batch I talked about before. And then the next line with MT update is like this momentum update where you say my gradient, kind of running average gradient, is the old gradient times beta 1, and then 1 minus beta 1 times the current gradient. And then as something new here, we actually also keep memory of the square of the gradient. So this GT to the square is actually kind of element wise squared of the gradient. And then there's an important point here why this Adam works so well, is that it actually corrects for the fact that M0, kind of our momentum, our stored memory for the gradient, is 0 at the end, at the beginning. So that means so that gives us a bias towards having a too small gradient. So that means that we can actually calculate a new kind of gradient direction, average gradient direction, M hat, which is corrected for this bias. And this is calculated, you can calculate that like a geometric series. So that is, you divide by 1 minus beta 1 to the tth power, where t is the number of gradient steps you have made in the end. And then your final update, then you actually normalize your step size by the kind of the square root of the kind of second moment of the gradients. Yeah, so this is more or less what I've said here. And this means that we kind of if alpha is now our step size in this paper, use alpha for what we call eta before, then actually we can show quite easily that our step size will never be larger than the step we take will never be larger than this alpha. So that's a way to kind of control that in all directions we have more or less the same step size, and we kind of know how big it is. And as I argue in the paper, it's kind of easy to more or less guess how big the step size should be. So that means that actually it turns out that you can actually more or less use Atom with more or less the kind of the default settings, and it would work with many problems. So this is kind of nice because the step size and these momentum terms are like kind of hyperparameters that take some time to find the right ones, and this algorithm actually kind of at least partially helps you to avoid spending too much time on hyperparameter tuning. For example, it could be that if you train with a constant step size, it would work fine in the beginning, but then after 100 steps, everything will explode, or you will not converge anymore, or you will kind of stop the convergence. And actually, with this kind of algorithms, you can kind of avoid that kind of headache. Yes, okay, so a little bit, I'll probably jump over this, but I'll leave that in the slides. There's a little bit of kind of theory, and also have some references to kind of analysis of convergence properties. So I'll just jump over this. And then here are some references, 2 places of references, and then thank you for your patience going so far.